Howdy, everyone. My goal for today, as I've said previously, is mainly to give you some time to work on the homework and ask questions in the chat as you do. If you have any questions at any point during this, just go ahead and drop them in the chat. In terms of announcements, I mentioned in the syllabus that there'd be a number of short quizzes. Next week on Wednesday will be the first short quiz, and the first short quiz will be on the extended Euclidean algorithm. It will just be, here are some numbers, do the extended Euclidean algorithm. You are more than welcome to use a calculator so that you do not have to deal with ridiculously large numbers by hand. And you're welcome to use a note sheet if you want, just so that you can have it written. Basically, I just want to make sure you're comfortable with the extended Euclidean algorithm, make sure you're getting through the content of the course. But there's not going to be any surprise questions on any of the quizzes. They're all going to be quite explicitly told to you in advance. Okay. Can someone put in the chat that you can actually hear me, just to make sure? Also, if you have any questions about any of that with regards to the quiz or topics or anything, let me know. Excellent. There are many upsides to YouTube, including the fact that this will be recorded in a way that is very easily retrievable. The one downside is that there's a pretty long lag between when you hear me say things and when I actually say them. So when we have these back and forth conversations, it can be a bit tricky. I did also want to mention the topic submission thing, which is coming up. So remember, you have to have chosen a topic by February 19th. That is a week from today. And with that topic, you have to include a one-page summary of your proposal. Okay. Now, it's always a little weird writing a proposal about what you're going to do with a project about something that you don't yet know. And of course, I don't expect you to magically absorb all of the material. But I want you to give me enough of an idea that you sort of have some specific questions that you want to answer, and then you want to share the answers with us. So if, for example, you chose as your topic Pell's equation, your one-page summary should say what Pell's equation is, and you should talk about how, okay, it looks like there's two ways to solve Pell's equation. One of them involves partial fractions, which I don't know what that is. One of them involves continued fractions, which I don't know what that is. And then some other one involves unit groups and some number ring or whatever. And so I want to understand each of these ways of solving this equation and how they're connected, or something like that. So when you're giving this summary, it is 100% understood that the summary is going to be lots of stuff of, I don't understand this, but I want to. But I want to make sure when you submit their proposal that there's enough hooks of things that interest you that you know what you're going to do when you start researching your project, okay, which will require at least enough research to provoke your curiosity to form those questions to write the one-page summary. You're not locking anything in stone, but you're giving yourself some direction, and then I can offer feedback on your proposal if I think one of your questions is ambitious, we'll say. And if you're looking for sources for something specific, depending on what it is, I might or might not be able to give you some recommendations of things that work. Okay. One bonus of the fact that this is number theory is that number theory is, as we've said many times, old, and so there is countless texts available for free online about these various topics. One hint you may or may not know is that whenever you're researching a math topic, usually the absolute best place that you can find material about it is in master's theses. So when a student is completing their master's degree, often they will choose a topic, and then they'll do a bunch of research about it, and then they'll write a paper about it, which is usually in the vicinity of 40 to 80 pages, depending on the exact topic. But usually, being master students, they're not yet so immersed in the topic that they're writing about that they assume you know lots of things that you don't. So usually they're very good papers in that they tend to not assume you already know anything you don't already know. And so if you find someone's master's thesis that covers your topic, that is usually an excellent place to start when you are looking for places to write from. Okay, so before we jump into homework, I wanted to, as a means of reviewing everything we talked about with divisors last time, talk about the proof of Euler's theorem. So I stated this at the end of last class, but Euler's theorem says that if you have an even perfect number, remember we don't know anything about odd perfect numbers, but if you have an even perfect number, it always has this particular form where this number is prime. Now, this is very similar to Euclid's theorem, which we proved last class, but it is different in that basically the if and then are reversed. So this is the converse to Euclid's theorem. So Euclid says if this number is prime, then this number works out to be perfect. What we want to prove is the opposite. If you have any even perfect number, then it already showed up from Euclid's theorem. Okay. So, as a proof of this, we're going to start by supposing n is even and perfect. No huge surprise, because the theorem we're proving says if something is even and perfect, then blah, blah, blah. So we're going to start by supposing n is even and perfect. And we're going to factor n. So I'm not going to completely factor n into primes. This is something you will often want to do. I'm only going to factor all the 2's out. So if I factor out enough 2's from any number, eventually the thing I'm left with is always going to be odd. Now, unique factorization actually implies the way of doing this is also unique. So you can always factor all the copies of one particular prime out of your number, and quite often in proofs, the thing you want to do is factor out all the copies of 2, so that you're left with 2 to some power times an odd thing. So let's remember what n is perfect means. N is perfect means that sigma of n, which remember is the sum of all of the divisors of n, is 2 times n, which is, in this case, 2 to the k plus 1 times x. Note, by the way, the fact that n is even is really just telling us that this k here is at least 1. Okay. You will see later why, if this k was 0, this proof does not actually tell you anything. Okay, so what this means, again, by our assumptions, is that the sum of the divisors of 2 to the k plus 1 times x, the sum of the divisors of 2 to the k times x is 2 to the k plus 1 times x. Okay. Questions so far? I'm going to pause for a good 30 seconds and let you catch up and let you catch your breath and make sure you agree with everything I've said or ask if anything needs clarifying. Okay, so now we're going to use the formula for sigma that we talked about last time. So sigma of 2 to the k times x. Remember, this is supposed to be the sum of all the divisors. Oh, sorry. Is it an issue if n is a power of 2, so that x is 1? So it is pretty easy to check that no power of 2 is perfect, because if I have a power of 2, the sum of the divisors is going to be 1 plus 2 plus dot 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 plus 2 to the k. And this is going to be 2 to the k plus 1 minus 1 by the geometric series formula. And note that in order for 2 to the k to be perfect, it would have to be 2 to the k plus 1, no minus 1, because it would have to be 2 times that. And so for purposes of this proof, nothing will break if x is 1, but we also won't find any perfect numbers where x is 1. So all the divisors of 2 to the k times x, they all look like some power of 2, that is 2 to the k or less, times some divisor of x. Those are the only things that I'm looking at here. So this is really a sum across 2 to the I times d, where d divides x, and I is less than or equal to k. Okay. This is what we did last time, where we said once you know the prime factorization of a number, you know all of its divisors very explicitly. They're all given to you in terms of things where you have an exponent of each prime less than or equal to the exponents present in the number. Okay. But last time we made a cute trick, which is that I can rewrite this times 1 plus x plus, and so I'm going to write here dot, dot, dot. This dot, dot, dot is all of the divisors of x other than 1 and x. Okay, so I guess I lied, David. I already have used the fact that x is not 1, because I am writing 1 and x as separate entries here in my list of divisors of x. And so the point here is that although this product looks horrifyingly messy, when I multiply this product out, I am always going to be getting one of the powers of 2 that I'm allowed to use times one of the divisors of x that I'm allowed to use. And in fact, I get every one of those combinations exactly once. Okay. So I'm going to simplify this by noting two things. One of those things is that I already said that because n is perfect, this is 2 to the k plus 1 times x. And because of the geometric series formula, this is 2 to the k plus 1 minus 1. You have to look at the screen to see what plus 1 minus 1 means. I'm going to take another pause as we look at this statement and make sure we're happy with where this came from. Again, I did two things. I used the definition of perfect, and I used the geometric series formula to clean up the powers of 2. Now, as it happens, this proof ends up being very, very on theme, because what I need to notice is that I have written 2 to the k plus 1 times x as a product, one of whose terms is 2 to the k plus 1 minus 1. And so what that means is that, in fact, 2 to the k plus 1 minus 1 divides this quantity. Again, that's just because I've written a product of two things that is equal to that. So both of these pieces divide the thing on the left. Okay, so all the prime factors of 2 to the k plus 1 minus 1 appear in either 2 to the k plus 1 or x. Possibly some combination, right? I don't know that this number is prime or anything like that. So there could be lots of factors, but all the prime factors of this number appear in one of these two pieces. However, which piece do they actually appear in? Both of those divide 2 to the k plus 1 times x. Yes, I agree. But this is the one I know slightly more about. And namely, the thing I want to use here is that this thing is odd. And because this thing is odd, no 2's can possibly divide it. And so, in fact, all the prime factors of this power of 2 minus 1, they all divide x. None of them can actually divide 2 to the k plus 1. And so, because 2 to the k plus 1 minus 1 is odd, no 2's divide it. And so what that means is that actually this 2 to the k plus 1 minus 1, it actually divides x. Again, I think this makes the most sense to think about in terms of the prime factorizations of both sides here. Okay. The prime factorization of the right-hand side, the one I'm pointing at, is some power of 2, namely the k plus first power of 2, times, and then a bunch of odd primes corresponding to x. Whereas the prime factorization of this piece, I know doesn't have any 2's in it, because it's odd, because a power of 2 minus 1 is always odd. And so what does that mean? That means all the prime factors that show up here, they all show up in the x part. None of them can show up in the 2 to the k plus 1 part. And so that shows you that actually all the prime factors in 2 to the k plus 1 minus 1, they are all prime factors of x. Can we get a thumbs up in the chat if that makes sense where that came from? Or a thumbs down if that does not make sense? Okay, I see a number of thumbs up at least. Okay. I'm going to go ahead and give this thing a name. Namely, I'm going to call this whole mess y. And so the thing I know is that, again, sorry, I'm not going to call that thing y. I lied. So, sorry. So because this is a divisor of x, that means that x is equal to 2 to the k plus 1 minus 1 times something. I'm going to go ahead and call the something y. That's all that being a divisor means, right? Is that there's something I can multiply this by to get x. Okay, so now I'm going to take this sigma that I had before. So remember, sigma of 2 to the k times x, it is 2 to the k plus 1 times x, which is now 2 to the k plus 1 times 2 to the k plus 1 minus 1 times y. But, on the other hand, it is also still equal to this sum that I had written before. So it is also still equal to 2 to the k plus 1 minus 1 times this sum of all the divisors of x. Now, one thing that you will note is in common between these two things that are equal is this 2 to the k plus 1 minus 1. And so when I divide that out, I get the equation that 2 to the k plus 1 times y is equal to 1 plus x plus dot, dot, dot. Now, I have to do something clever. Which is I have to use the fact that x is, sorry, yes, okay. So I have to use the fact that this x is 2 to the k minus plus 1 minus 1 times y. So this is 2 to the k plus 1 times y. Sorry. So this says 2 to the k plus 1 times y is equal to 1 plus 2 to the k plus 1 minus 1 times y plus dot, dot, dot. Okay. So what you may notice is that things are starting to look rather similar on both sides of this. So I am going to get 2 to the k plus 1 times y is equal to 1 plus 2 to the k plus 1 times y minus y. There we go. But this term is now on both sides, so I can subtract it. So I now get the equation 0 is equal to 1 minus y. So y is actually 1. So now we have to unwind what saying y is actually 1 means. So since y is 1, that means x is 2 to the k plus 1 minus 1, full stop. And so that means our original number, n, is equal to 2 to the k plus 1. Sorry, 2 to the k, right? Yes, our original n is 2 to the k times, and then 2 to the k plus 1 minus 1. Okay. Which looks an awful lot like the desired form, you'll notice. Okay. Namely, I have a power of 2 times, and then the next higher power of 2 minus 1. So the only thing I need to finish the proof is to convince you that this number has to be prime. And why does that number have to be prime? Well, I actually cheated slightly when I went from this page to this page. Namely, I just dropped this plus dot, dot, dot. Remember where this plus dot, dot, dot comes from, though. This plus dot, 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 this is all the divisors of x other than 1 and x. But if there are any more things here, then when I subtract stuff over to this side, my y will end up having to be even less, and that will not work out. Okay. And so it has to be the case. The only way that these things can possibly end up being equal is if this dot, dot, dot that I omitted is actually 0. But what does it mean if that dot, dot, dot is 0? Well, it means exactly that x is prime, because x can't have any other divisors. Okay, so that is the proof of the other direction here. Okay. Again, we're using this trick heavily that as soon as I know a number's prime factorization, I know what all of its divisors are, and that lets me write things like the sum of the divisors, or the number of divisors, as we did last class, as this sort of product, and then everything sort of falls out from there. Okay, so I will leave it to you to ask questions about this proof, if you would like, or if you have other questions that Or if you have questions from the homework, basically my intent was that you start working on the homework and ask me as you have questions. So whatever you put in the chat, I am happy to talk about. Yes, so this is a good question. What is the greatest common divisor of three numbers? And the greatest common divisor of three numbers is the largest number that divides all three of the numbers. So be aware when you see GCDs of three numbers that it might be that the GCD of three numbers is 1, even though every pair of them have a common factor. So, for example, the GCD of 6, 4, and 9 is 1. Oh, I guess that wasn't a great example because these two don't have a common factor. Let's fix that. The GCD of 6, 20, and 45 is 1. There is no number that divides all three of them other than 1. But every pair of these have something in common that you would have to worry about. So be a little bit careful when you see GCDs of three numbers, because 90% of the time you see a GCD, it's of two numbers. And so some things that you get used to working don't actually work well with three numbers. Okay, so how many steps does it take to do this? So we have to decide what we're counting as a step. If I did this, I would say x, y, a. Sorry, it would be 12x plus 6y, so 1, 0, 0, 1. So that's 12, that's 6. And then the next step is I subtract 2 from here, and so the next thing I will get is 0 here. So I would call this 2 steps. But you're welcome to disagree and call this 1 step if you prefer, but I think it makes sense to count all the lines of the table before you get to 0 at the end. But I agree that I could have clarified slightly, but I think if there's an off by 1 error because we disagree about what a step is, I'm still going to be happy. Alrighty, folks. I think that brings us about to the end of class for today. If you have any questions for the homework, be sure you can ask them on Monday. Remember, the homework is due Wednesday, so you can ask them in class on Monday or in office hours on Tuesday. The link for office hours, by the way, is the same as the link you used to get here today, so you have that for the future. Have a wonderful weekend, be safe, and I will see you on campus on Monday. Ta-ta for now.